Hello, I am Seema and welcome to part 39 of the chapter Hydrocarbons. We have been studying about aromatic hydrocarbons and we did the nomenclature and isomerism of hydrocarbons in part 38. In this video, I'm going to talk about the structure of benzene, and this is going to be a very interesting video because it involves a story in it, and I find stories, when you relate stories to certain topics, it becomes very interesting. Well, talking about the structure of benzene, we know the formula of benzene is C6H6, and the structure of benzene for a very long time, for years altogether, it was unknown. And the scientists could not fathom what the structure of benzene would actually be like. Benzene had very different properties from the alkenes. They had studied certain properties and they knew that benzene should be unsaturated, and benzene should have, since it is ENE, it has alkene, that is double bonds in it. But it had certain properties which were very different from regular alkenes, and therefore the structure obviously had to explain those particular properties, and scientists yet could not think of a structure. And even the formula of benzene was such that it could not satisfy a normal aliphatic alkene structure. So, but they could not think of the structure for a very long time. So let us just start studying about it. Benzene was isolated by a scientist called Michael Faraday. You've heard about him. By Michael Faraday in 1825. In 1825, he separated benzene and he isolated it and he named it. He said, okay, this is a certain compound and it's different from the other alkenes. And the molecular formula was also found out, that it has a molecular formula of C6H6. It has 6 carbons, it has 6 hydrogens. And the molecular formula, what did it indicate? It indicates that there is a large amount of unsaturation. You know, for a saturated alkane, that is for an alkane, if there are 6 carbons, the general formula for alkanes is CnH2n plus 2, which means if C is 6, hydrogens should be 2 into 6, 12 plus 2, 14. There should be 14 hydrogens. But this has only 6 hydrogens, what does this indicate? That there's a lot of unsaturation in this molecule, which means a lot of multiple bonds in this molecule. So, the molecular formula indicates a high degree of unsaturation. And due to its unusual stability, not only was this indicated that it has a lot of unsaturation, unsaturated hydrocarbons should not be stable. That is what we have studied in the previous videos, that alkenes and alkynes, they show addition reactions, they really undergo reactions very quickly because of the unsaturation. But benzene, on the other hand, shows an unusual amount of stability in spite of such a large amount, such a great amount of unsaturation in it. So it is not usual to have that kind of a stability. It was an unusual stability and it had unique properties, and therefore it took many years to assign it its structure. It took many years for scientists to understand what could be the reason. They could really not make out why was there so much of unsaturation and yet there was so much of stability. Why did it show properties different from the regular alkenes? And therefore, it took a long time. And how it was done, let us first see 2 properties where it was different. C6H6, that is benzene, it forms a triozonide. When we studied alkenes, we have studied about the reaction ozonolysis, that is the reaction with ozone, and it results in the formation of an ozonide as an intermediate. Please refer to the video where we did alkenes and you will see the chemical properties of alkenes. You will have this reaction. So I would suggest you watch that video and see how the ozonide is formed as an intermediate. So wherever there is a double bond in an alkene, an ozonide is formed as an intermediate. And in the case of benzene, a triozonide was formed, which means 3 molecules of ozone were being added up to the benzene molecule, which indicates that there must be 3 double bonds in benzene. So of course, when we said it is highly unsaturated, yes, it has 3 double bonds. In just 6 carbon atoms, it had 3 double bonds. The second property that was very unusual about it, or what was noticed, was that it produces only one mono substituted product. If you substitute any one of the carbon atoms, the product that you would be getting is only one, which means that all the carbon atoms and all the hydrogen atoms are identical. The structure is very, very symmetrical, and all the carbons and all the hydrogens should be identical. Remember, until now, only aliphatic hydrocarbons had been discovered. There was no idea about the cyclic hydrocarbons. So, if you imagine this structure now, if you imagine benzene to be the 6 carbon atoms, and let me say C6H6, CH, and it has 3 double bonds, so let us make alternate double bonds. CH, single bond, CH, double bond, CH, single bond, 3 carbons, 4 carbons, 5 carbon, CH, and 6th carbon, CH. Single, double, 1, 2, 3, 4, 5, 6. Are there 3? No, there should be 3 unsaturated bonds. So there should be 3 double bonds. So a double bond here, a double bond here, and a double bond here. So according to whatever we have understood now, benzene should have 3 double bonds because it was forming a triozonide structure. It had 3 ozone molecules added to it, so the 3 alkenes should be there. Now, what is the problem with this structure is that every carbon in a hydrocarbon should form 4 bonds because it is tetravalent. And we find that all these carbons in the middle of the chain, they do form 4 bonds, 1 bond with hydrogen, 2 bonds with the carbon on the other side, and 1 bond with the carbon on the other side. So all of these carbons are forming 4 bonds. But the terminal carbons, they are forming only 3 bonds. 2 bonds with the carbon here and 1 bond with hydrogen, so it needs to form 1 more bond. Similarly, the carbon here is forming 2 bonds with this carbon and 1 bond with hydrogen, and it also needs 3 bonds in total. It also needs to form 1 more bond. So the structure was intriguing, and the scientists couldn't understand how do we satisfy this? How do we make a structure that can explain this, or maybe rearrange it in such a manner that since there were 3 double bonds, as you just noticed, if I put the single bond here, I would get only 2 double bonds. So if there were 3 double bonds, this had to be the structure. So on the basis of whatever the understanding was, that it will form a triozonide, that it forms only 1 mono-substituted product, which means that these 2 carbons, according to this structure, are different because they are terminal carbons. And these are the carbons of the chain. So according to this, the second property, the 2 terminal carbons also should be like the other carbon atoms. They should also form 4 bonds, they should not form 3 bonds. So, and that should not leave dangling electrons, 1 electron which is left to 1 valency which is not satisfied. That should not happen. And since this structure, the benzene molecule was neutral, obviously this valency was being satisfied. These terminal valencies were being satisfied somehow. So there was this scientist called Kekulé. And Kekulé, Auguste Kekulé was a professor in Darmstadt, Germany, and he became a professor in 1856, and he was a fellow of the Royal Society in 1875. He is the person who in 1865 proposed the structure of benzene. And this is where the story comes in, it's a very interesting event. What happened? Kekulé was the person who gave the idea of his contribution in the field of the structural chemistry is pretty high. And what happened was that, let us first come back to the story. He was really struggling to find the structure of benzene, and he already knew this and these 2 properties, and he was this is where he had reached. So once he was sitting and writing in his textbook, and while he was writing in his textbook, in his mind, he was constantly seeing these molecules, because when you work on something with a great fervor, you tend to start obsessing about it. So that was the state he was in. He was obsessing. He was only thinking about these molecules. What could the structure be? He's struggling to find the structure for years and years. He's trying and he's not reaching anywhere. Ultimately, one day when I was writing in his textbook, he shuts it down. He just stops it. He turns his chair towards the fireplace and just relaxes and goes off to sleep. And when he goes off to sleep, usually when we are thinking a lot about something and we go off to sleep, we tend to have dreams about that thing also. Have you ever noticed this? So what happened was, when Kekulé went off to sleep, he starts getting dreams of these molecules, these little structures of molecules, little carbon chains. By this time, Kekulé was the person who had talked about the catenation, who had introduced the concept of catenation in carbon atoms. Catenation was the property of carbon atoms by which they could form long chains, and that is why he had reached this structure. So he imagined, little chains swimming around, little chains of molecules swimming and swimming around, and the little chains of molecules, they kind of went into the background. They went a little away, and the longer chains, they started coming and floating in front of his eyes. In his dream, they come to the front. And when these longer chains, they come, they start mingling and tingling like this. They, like snakes, they are just swimming around each other and they are going and tangling with each other. And what he suddenly notices is that one snake puts its tail in its mouth. One of the snakes puts its tail in its mouth. As soon as the snake puts his tail in his mouth, and what he is seeing is the molecules, he suddenly wakes up from his dream. And when he wakes up from his dream, it is like that, it's like that idea that he has got. Oh my God, I never thought about this. How would it be if this carbon had one dangling electron, one unfulfilled valency, and this carbon also had this unfulfilled valency, if the first carbon and the last carbon form a single bond among each other? That is, if this is the mouth of the snake and this is the tail of the snake, if I put the tail of the snake into the mouth, that is, I make a bond between these two, then these terminal valencies would be satisfied. If they will be satisfied, it means that benzene has a ring structure, the structure of a ring. So this ring structure of benzene was imagined by Kekulé, that it is forming a ring. And this was the most beautiful thing, because this was a breakthrough. And now, imagining the ring structure, he started thinking that if this is the structure, can these properties be explained? So let us now study what he said. But another thing, he then confirmed about the properties of benzene, and only then he said that yes, this could be a possible structure. He did not just think that, okay, so I saw a snake put its tail back into its mouth and therefore this has to be. No. Once he made the structure, he confirmed that yes, this could be responsible, but the structure that he gave was not the ultimate structure, was not completely right, but it was a step in the right direction. So it's very interesting. He gave a statement many years later about this dream, and I would like to read this statement because it involves a very important lesson. He said, "I was sitting writing at my textbook, but the work did not progress. My thoughts were elsewhere. My thoughts were somewhere else. I turned my chair to the fire and slept. Again, the atoms were gamboling before my eyes. This time, the smaller groups kept modestly in the background. My mental eye rendered more acute by repeated visions of this kind. Since the same vision was being repeated, his mental eye started focusing on it. It became more acute. So my mental eye, rendered more acute by repeated visions of this kind, could now distinguish larger structures of manifold conformations. He could now, his mind's eye could see larger structures of many different kinds of conformations. Long rows, sometimes more closely fitted together, all twisting and turning in snake-like motion. But look, what was that? One of the snakes has seized hold of its own tail. And the form whirled mockingly before my eyes. It was as if that snake held its tail and it came and it was kind of teasing him in front of his eyes. It came mocking in front of it whirled mockingly in before my eyes. As if by a flash of lightning, I woke. I spent the rest of the night working out the consequences of the hypothesis. That he thought, what would be the consequence if this carbon attaches itself to the first carbon and the last carbon, form a bond and form a ring-like structure. Let us learn to dream, gentlemen, and then perhaps we shall learn the truth. But let us beware of making our dreams public before they have been approved by the waking mind. This last sentence is so poignant. It's so important. It says we must learn to dream because most of our ideas, the best of your ideas, you may get when you are in a dream. You may get in the form of a dream. But remember not to share your dream with the whole world before you confirm what you saw with a waking mind. When he had the dream, he did not run to the world to tell, okay, Eureka, I found my answer. No, he woke up, he worked on that. He started making that structure. He started trying to verify if this structure is possible. So when the waking mind thought about it and he was convinced that yes, this could be the right explanation for the structure of benzene, only then he told the world. So whenever we are also, there's a lesson in this, whenever you are also working on something, when you get an idea, do not just jump and say that, okay, I found it. First, confirm it with your waking mind, with your alert mind, and then when you're convinced, that is the time to share it with the world. So now, what is the structure of benzene that Kekulé made? He said that C6H6, it has a cyclic arrangement of 6 carbon atoms, and these 6 carbon atoms have alternate single and double bonds. Do you see? There were 3 double bonds, but there were 2 single bonds. But with the first and the last carbon making a single bond, now there are 3 single bonds and 3 double bonds. So they were alternating single and double bonds. So with alternate single and double bonds, and 1 hydrogen atom was attached to every carbon. As soon as this structure was made, the valency of each carbon was satisfied. Every carbon was now forming 4 bonds, which clearly explains that in all hydrocarbons, every carbon should be forming 4 bonds. And that was happening now. So this structure of benzene is simplified and it is shown as this, where every corner of the hexagon signifies a carbon, and it is understood that hydrogens are attached to the carbon to complete that, to satisfy the valency of 4. And the alternating double bonds are shown in this hexagon by drawing the alternating double bonds. Now, if you imagine this to be the structure, this or this, it is the same thing, to be the structure of benzene, then if you have two substitutions at the ortho position, that is, if you have a di-substituted product, that is 1,2-dibromobenzene, you should get 2 different kinds of 1,2 isomers of 1,2-dibromobenzene according to this structure given by Kekulé. Why? Imagine if this is the first carbon and this is the second carbon, bromine and bromine add here, there's a single bond between the two. But since all carbons are identical, I could take this as the first carbon and this as the second carbon. So if the 2 bromines attach here, then there is a double bond between the 2 carbon atoms. So you should get 2 different kinds of di-substituted products. But it was found that there is only 1 di-substituted product. Benzene does not have 2 different di-substituted products. One where there is a single bond between 2 carbons and one where there is a double bond between the 2 carbons. This doesn't happen. So this structure indicates two isomeric disubstituted 1,2-dibromobenzene structures should be there. That is one where the two bromines are attached to two carbons with a double bond, and one where the two bromines are attached to two carbons with a single bond. But it was found that there is only one disubstituted product, ortho product of benzene. How did Kekulé explain this? Kekulé could not explain this, and he said that maybe that these two forms, there are two forms of benzene, and they are resonance. They have, sorry, not resonance, they are canonical, what should I say, they are kind of interchange. They kind of oscillate between the two structures, right? So I don't want to get ahead of myself because that's the next topic. So here he said that there are two structures where the double bonds are alternating, of course, but the alternating, I made two bonds along the same, okay, alternating, yeah. So he said that these double bonds, they kind of interchange. Between the first and second carbon, there's a double bond. In another structure, the other isomer, you will have the single bond between those two carbon atoms. And since these structures keep changing, the double bond keeps changing like that. Therefore, you get only one disubstituted ortho product. So he explained this by oscillating double bonds, that the double bonds in benzene, they oscillate. So this is how he showed that the double bond is here, and here the double bonds have shifted. So, but this structure also, this concept of the oscillating double bonds also could not explain why is benzene so stable? Why is it so unusually stable? Even if the double bonds are oscillating, it is still a highly unsaturated compound, and therefore it should show a lot of addition reactions. But benzene has been known not to show addition reaction but to show substitution reactions. That is, it kicks out the hydrogens and the group that is adding, it gets substituted in place of the hydrogen. It does not break the unsaturation. So there is something about these double bonds, these alternating double bonds, which are rendering a lot of stability to benzene, which Kekulé could not explain at that time, and which was later explained by a phenomenon known as resonance. And that will be the topic of our next video, where I'll be telling you what resonance is. So this structure this idea of oscillating double bonds could not explain its unusual stability and its preference for substitution reactions instead of addition reactions. And that was explained by the next concept, that was resonance. And the resonance hybrid, the structure of the resonance hybrid then became the final structure of benzene. So we will be continuing our study of the structure of benzene and understanding resonance in the next video. With this, I'll wrap up today's video. If you wish to watch other videos of this chapter, please click the link that appears on the top of your of the video. And if you found this video helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.